Hey, Math 30-2s. Today we're going to look at combinations part 2. So problems that occur with the words at least, at most, etc. Alright, so let's look at the first example. The student council decides to form a subcommittee of 5 council members to look at the funds raised, or how funds raised should be spent on the students at the school. There are a total of 11 students, council members, 5 male and 6 female. How many different ways can the 5-member subcommittee be chosen if there are no restrictions on the number of males or females? Well, we've got 5 males, 6 females, so that's 11 students, and we need to choose a 5-member council, so we're going to choose 5 of them. And order for a council is important or not. Order is not important, so this would be a combination. So 11 combinations of 5. So you can do that in your calculator. 11 combinations of 5 is 462 possible 5-member subcommittees. Part B says exactly 3 females. So that means we need 3 females, and it's a 5-member committee, so there must be 2 more people on it, and they must be males to have exactly 3 females. So we've got 6 females and combinations because order is not important, and we need to choose 3 of them. And to finish off this committee, we're going to multiply. I have got 5 males, and I need to choose 2 of them. It's a combination because order is not important. So this gives me my 5-person committee: 3 females, 2 males. All right. Use your calculators, figure that out. 6 combinations of 3 is 20. 5 combinations of 2 is 10. 20 times 10. There are 200 subcommittees with exactly 3 females on them. Part C. How many 5-person subcommittees are there if at least 3 females are on the committee? So at least 3 females. Well, we did 3 females and 2 males. Or there could be 4 females and 1 male. Or you could have all 5 of the members be females and no males. So that's at least 3 females. All right. So let's go through the situations. We did the 3 females, 2 males earlier. 6 females, we need 3 of them. 5 males, we need 2 of them. Order is not important. So that's the 6 females, 2 males. Or indicates addition. Another committee that would satisfy the situation would be 4 females. So I've got 6 females to choose 4 of and 1 male. So we're going to multiply to make this committee work. I've got 5 males. I need to choose 1 of them. So that situation where we've got 4 females and 1 male satisfies the condition of having at least 3 females. Or, so we're going to add, we could have a 5-female committee and no males. So I've got 6 females. I would like to choose 5 of them. I've got 5 males. I want to choose none of them. All right. So there's all the situations that satisfy at least 3 females. All right. We've got 3 females or 4 females or 5 females. So now it's just a matter of calculating. We did this one already. 6 choose 3 is 20. Times 5 choose 2 is 10. Add that to 6 choose 4, which is 15. 15 times 5 choose 1, which we know is 5. And finally 6 choose 5, which we know is 6. Multiplied by 5 choose 0, which is 1. So we get 200 plus 15 times 5 is 75. Plus 6 times 1 is 6. So the number of subcommittees would be 281 that have at least 3 females. Great. Let's look at example 2. Consider a standard deck of 52 playing cards. How many different 5-card hands can be formed with no conditions? So we've got 52 cards in the deck. I need 5 card hands. And does it matter the order the cards are dealt to you? No. So this is the combination. 52 combinations of 5. You do that calculation, put that in your calculate, you get 2,598,960 possible 5-card hands. How many 5-card hands can be formed with at least 4 red cards? So that means I could have 4 red and 1 black. That satisfies. Or I could have 5 red cards and no black. That satisfies the condition of at least 4 red cards. So now let's go through. I need 4 red cards. In the deck of 52, 26 or half of them are red. Order's not important. I'm going to choose 4. Multiply that by, there are 26 black cards, and I want to choose 1. So that situation satisfies the condition of at least 4 red cards. Or, we now add, this situation satisfies the condition of at least 4 red cards. It's 5 red cards. So, we've got 26 red cards. I want to choose 5. And we've got 26 black cards. I don't need any of those. So we now simplify. 26 choose 4 is 14,950. 26 choose 1 is 26. That satisfies the conditions. Or 26 choose 5, well, 65,780 times 26 choose 0 is 1. All right. So multiply that out and you add them together, we get 480 possible 5-card hands that have at least 4 red cards. What about part C here? How many different 5-card hands can be formed with at most 2 kings? So at most 2 kings, well, we could have 0 kings and 5 not kings, or we could have 1 king and 4 not kings, or finally we could have 2 kings and 3 not kings. All right, now not kings, I guess we want to use the notation we've learned earlier. Let's not go with not kings like that. Let's just go not kings. That'll work. All right, so let's calculate this out. I have got 4 kings in the deck. I want to choose 0. That leaves 48 of the 52 are not kings. I want to choose 5. That satisfies having no kings and 5 other cards. Or we could have 1 king. So I've got 4 kings in the deck. I want to choose 1. Again, order's not important, so it's a combination. Multiplied by, I've got 48 not kings. I now want to choose 4. Or, we're going to add to that, I've got 4 kings. I want to choose 2. And I've got 48 not kings. I want to choose 3. So now it's just a matter of calculating that out. So you can use your calculators, or you could follow along and write down what I get. All right. So 4 choose 0 is 1. 48 choose 5 is a rather large number. 1,712,304. Or means addition. 4 choose 1 is 4. Multiplied by 48 choose 4 is 194,580. Or 4 choose 2 is 6. And 48 choose 3 is 17,296. Right? So you could work that out. You come up with 2,594,400 possible 5-card hands that have at most 2 kings. Now if you look up at the one with no restrictions, we're looking at it's pretty close to almost all the possibilities. So there aren't too many that have more than 2 kings. Next page. Using the complement to solve at least and at most problems. Sometimes using complementary outcomes can reduce the workload in at least or at most problems. If we look at class example number 1, in which there were 462 ways in which a 5-member subcommittee could be chosen from 5 males and 6 females. Students were asked to determine how many of the 462 possible subcommittees contain at least 1 female. Brandon used the method of class example 1 to solve the problem, complete his work. So he said you could have 1 female and 5 males, or we could have 2 females, 3 males, or 3 females and 2 males, 4 females and 1 male, or finally 5 females and no males. So he goes through all these situations. 6 choose 1 for females, 5 choose 4 for males, and so on and so on. He wants us to complete this work. So 6 choose 1 times 5 choose 4. Well, 6 choose 1 is 6, and 5 choose 4 is 5. So I'll just multiply those out. 6 times 5 is 30. That's the way we can have 1 female, 5 males. 2 females and 3 males. 6 choose 2 is 15. 5 choose 3 is 10, so that's 150. Plus 6 choose 3 is 20. And 5 choose 2 is 10, so that's another 200. Plus 6 choose 4 is 15, and 5 choose 1 is 5, so that's another 75. And 6 choose 5 is 6, and 5 choose 0 is 1, so that's another 6. So if you add all those up, we get 461 possible ways. Alicia in part B realized that there was a quicker way to solve the problem by using complementary outcomes. She partitioned the 462 subcommittees into 6 groups. Complete her work below. So, total number of committees to be selected, the total would be, if you could have 0 females and 5 males, or 1 female, 4 males, or 2 females, 3 males. You could have 3 girls and 4 boys, or 4 girls and 1 boy, or 5 girls and no boys. That's every possibility. Now you notice the work above is all this, right? Having at least 1 girl. So the number of ways to select at least 1 female, we did that work up there, that's 461. Number of ways of selecting 0 females and 5 males. Well, if you did that work, that would be 0 females, we've got 6 choose 0, and 5 males, 5 choose 5. So 6 choose 0 is 1 times 5 choose, sorry, you need all 5 of those. 5 choose 5 is also 1. So there's one way to get that. So number of ways of selecting at least 1 female would be the total number of ways, right? At least 1 female, we're going to keep that by itself. The total number of ways, subtract this one, right? So the total number of ways is 462, minus the number of ways to select no females was 1, right? We just figured that out. Number of ways of selecting 0 females and 5 males, that's one way. So the number of ways of selecting at least 1 female would be 462, take away 1, which is 461. So that's a lot quicker. We already knew this was 462 from previous work. So in Alicia's work, the outcome is the complement of the required situation that was asked for. So in general, put a big star beside this, the number of ways for the required outcome is going to equal the number of ways with no restrictions, subtract the number of ways for the complement of the required outcome. So when writing the solution to a similar problem, the first 3 lines of Alicia work may be omitted. So we look up here. You don't have to write them all out and then figure that out. You just want to show this step and down. All right, we understand complements, we can go from there. Okay, so let's have a look at example 3. Consider this question: a standard deck of 52 cards. How many different 5-card hands can be formed containing at least one club? So we could do this the long way. Say 1 club and 4 not clubs, 2 clubs and 3 not clubs, 3 clubs and 2 not clubs, and so on and so on. Or we could say number of ways of selecting at least 1 club in your 5-card hand should equal the number of ways where there's no restrictions subtract the number of ways which is the complement of having at least 1 club. What's the complement of having at least 1 club? Well, that would be having no clubs. So if you take all the possibilities where there are no restrictions and subtract from that the complements of having at least 1 club, we should be left with how many hands have at least 1 club. So no restrictions, we've done that. There's 52 cards in the deck. We want to choose a 5-card hand. It's combinations because order is not important. From that, we're going to subtract the probability of having no clubs, the number of hands, of having no clubs. Well, there are 13 clubs in the deck. That means there's 39 not clubs. And we need to choose 5 of those. So now that's calculator work. 52 choose 5, subtract 39 choose 5. All right? So if you do that, you get 2,023,203. There's the number of 5-card hands that have at least 1 club in them. All right? So the idea of a complement makes us have a lot less work. Let's look at combinations which are equivalent. Fran and Bernie have identical collections of vintage toy vehicles. Fran selects 2 toys from the 10 shown for the display in her cabinet. Since the order of display does not matter to her, she calculates this as 10 choose 2 or 45 ways. Bernie decides to select 8 toys from the 10 shown to display in his cabinet. Since the order of display does not matter to him, he calculates this can be done 10 combinations of 8 ways, which is also 45. Explain in words why 10 combinations of 2 is the same as 10 combinations of 8. Interesting. Well, we could say that by selecting 2 toys to display from the 10, let's say you select these 2, you're also really selecting 8 toys, maybe these 8, to take out of the cabinet, right? So 10 combinations of 2 is the same as 10 combinations of 8. Use factorial notation to show that 10 combinations of 2 is the same as 10 combinations of 8. So let's use that factorial notation. So using factorial notation to show this, 10 combinations of 2 in factorial notation would be 10 factorial. It's got it on your formula sheet, or it's got it in the previous lesson. All divided by n minus r, so 10 minus 2 factorial, and r factorial, 2 factorial. So if I simplify this, I get 10 factorial over 10 minus 2 is 8 factorial, 2 factorial. Well, let's do the same thing and have a look at 10 combinations of 8. Well, 10 combinations of 8 would be n factorial over n minus r factorial, r factorial. So we get 10 factorial over 10 minus 8 is 2 factorial, 8 factorial. And we can see those are identical. All right, it doesn't matter what order they're in. They're going to be the same. If you go to your calculators, they're both going to give you 45. All right. C, give another 2 examples of equivalent combinations similar to the one above. So 2 more examples. You go ahead and think of 2 more. I'll give you one right now. How about something like, oh, let's say 18 combinations of 7 should equal 18 combinations of 11. You come up with one more. So these examples up above are a representation of this general rule. N combinations of R is the same as N combinations of N minus R. Or sometimes you'll see combination notation written with parentheses. Right? So now algebraically prove that this is true. So you've got your notation. N combinations of R, well, that would be N factorial over N minus R factorial. And that is supposed to equal N combinations of N minus R, which is written as N factorial over N minus R. Well, in this case, R is N minus R factorial, and R, which is N minus R factorial. So it looks something like that. Well, the left side is about as simple as we can get. Let's simplify this right side of this equation, and that's how we do a proof. So we get N factorial over N minus R. Well, this negative sign should go to both terms here, so N minus N is gone, minus a negative R, just leaves us with R factorial, and N minus R factorial. So we can see they really are the same. The denominators are written in a little different order, but they are identical. All right. So if you go right from your notation formula, combination notation formula, you're going to get the same thing. Great. Let's look at example 4. Solving for N in combination problems. During a Pee Wee hockey game, actually during a Pee Wee hockey tryout, all the players met on the ice after the last practice and shook hands with each other. There were a total of 300 handshakes. Write an equation involving combinations whose solution would determine the number of players on the ice. So we're saying this is combinations because order of shaking hands doesn't matter. I shake your hand, you shake mine. We're both shaking hands. The order is not important, so it's a combination situation. So what we do know is, in total, there are 300 handshakes. We know it's a combination situation. We don't know how many people are on the ice, but we know it takes 2 people to shake hands. So we're looking for N. How many people are on the ice? Solve the equation in part A above by guessing and checking, and then by using factorials. All right? So you could go ahead and do some guessing and checking on your own. Try some values for N until you get something that gets close to 300 and narrow down. All right? If you don't like to guess and check, then here's how we do it using factorials. N combinations of 2 is supposed to equal 300. So I can rewrite N combinations of 2 as N factorial over N minus R factorial, R factorial. That's supposed to equal 300. And then I could say, well, that's the same as saying N factorial over, let's start writing the N factorials, N times N minus 1 times N minus 2. There we go, factorial over N minus 2 factorial. And 2 factorial is 2 times 1, so that's just 2. And that should equal 300. Now I can reduce any numerator to any denominator. You divide N minus 2 factorial by N minus 2 factorial, we get 1. So I'm left with N times N minus 1 divided by 2 equals 300. Now to get rid of this denominator of 2, I'm going to multiply both sides by 2. So I multiply both sides by 2 to get rid of that denominator of 2. That's gone. I'm left with 300 times 2, which would be 600. And on the left side, it's N times N minus 1 equals 600. All right? Now we can solve this a bunch of different ways. If I expand this out and set it equal to 0, I get n squared minus n minus 600 equals 0. That's a So I now solve this by factoring, and I get n minus 25 times n plus 24 equals 0. Set each factor equal to 0, we get n equals 25, or n equals negative 24. Now this one doesn't make any sense in the context of the problem. We can't have a negative number of people on the ice, so our best answer is 25. So we would say there's 25 players on the ice. Now you could have got that by guessing and checking as well, but there's the combination method using your formula. All right, so you guys have your assignment, questions 1 through 9. Away you go.